all, I'd like to thank all organizers for inviting me to this wonderful workshop. And today I'm gonna talk about how to learn three-dimensional topology via graph neural networks. So this talk is based on this paper, Graph Neural Networks and Three-Dimensional Topology, which is the joint work with Pavel Petrov, who is actually my PhD advisor in ISTP. So when I was a PhD student back then, I studied kind of quantum topology, more specifically like G-hat invariance for Plum3 manifolds. I tried to extend the mathematical definition of G-hat invariance to larger class of Plum3 manifolds. So let me briefly introduce G-hat invariance, but not that deeply. So originally, this G-hat invariance is predicted in the physics, the three-dimensional n equal to 2 SUS theory. It has kind of interesting points in both in physics and mathematics. So in physics, it is realized as the index of BPS states in string theory and M theory. And in mathematics, they are kind of some invariants of certain class of three manifolds, not all three manifolds. Yes, so in physics, it's kind of, it can count the BPS states in string theory and M theory. And in mathematics, they are kind of invariants of, say, Plum3 manifolds. And conjecturally, it would be kind of categorification of WRT invariants for three manifolds. So here, the categorification means it can be some linear combinations of radial limits of Q series. But unfortunately, a rigorous mathematical definition is yet to be found. So, okay, so in order to just introduce some notations, I will briefly introduce some. So we have climbing graphs, which is a finite weighted graph, integer weighted graph. So we have like finite number of nodes and edges and integer data associated to each node. And then there is a mathematical way to construct corresponding three manifolds from the priming graph. So starting with the graph, we associate n node, simple n node to each node. And then we make kind of Hopf link whenever two nodes are connected by an edge. So for example, this A1 node and A2 node is connected, then we make Hopf link between A1 n node and A2 n node. Then we get kind of framed links. Then we perform dense surgery along the framed links. Then we get kind of oriented and closed three manifolds, which is called sometimes Plum3 manifolds. So in this talk, we only consider the priming trees, so which means priming graphs without any cycles, just for simplicity. Okay, then interesting point here is that two different priming graphs can represent the same three manifolds up to homeomorphism, if and only if they are related by finite sequence of Newman moves. So here is three types of Newman moves, which is corresponding to three-dimensional Kirby moves. So usually we call like blow down move from upper priming graph to the downside priming graph because we eliminate the one vertex. And then the other side is from the downside priming graph to upper priming graph is called blow up because we create one node. So we have like five blow down moves and 5 blow up moves, counting the signs. So G-hat invariant, so G-hat is Q series. This Q series is kind of invariant of Plum3 manifolds, which means it is unchanged under the Newman moves to the priming graphs. So this is the exact, some kind of mathematical definition of G-hat invariance. Well, I will not explain in detail, but what I'm going to stress is that this G-hat invariant formula is well defined only for, say, weakly negative definite plumbings, which means it is a plumbings whose linking matrix is invertible, and this inverse matrix is negative definite on the subspace corresponding to the vertices of degree larger than 2. This kind of vertices is coming from the exponent of these rational functions. Well, I believe that Brandon will introduce in detail in the next talk. Okay. So as I told you, this G-hat invariant is only for weakly negative definite plumbings. Then how about generic plumbing trees? Then we have no idea to distinguish whether two plumbings represent the same manifold or not. So machine learning and deep learning provides us kind of this answer to this question. So since we are dealing with topology, it is natural to use geometric deep learning instead of using usual neural network and deep learning. So fundamentally, geometric deep learning involves kind of how they provide the way to how to encode the geometric understanding of data, like grids and groups and graphs and geodesics and gauges. They are called kind of 5Gs of geometrical deep learning. But in our case, we are dealing with planning graphs, so it is natural to use graph neural networks. So here is the chart for 5 most appeared keywords in a ICLR, which is kind of International Conference of Learning Representations. I think it is one of the hottest conference in machine learning area. So as you can see, the reinforcement learning and graph neural networks still remains a hot topic, even as the large language models such as ChatGPT dominates all the spotlight. So we will apply these 2 keywords, RL and graph neural networks, to realize 3 manifolds. So here is a simple introduction to 3 flavors of GNN layers. The first one is called graph convolutional network, simply GCN. So this GCN is designed to learn the node feature by simply aggregating from the node features in the neighborhood. So this red colored node, in order to get the node representation of this red colored, we aggregating the node features from the neighborhood nodes. And then the second type of graph neural networks is called attentional. So one of the examples is graph attentional network, which is simply called GAT. This model is also aggregating the neighbors node representations, but we introduce some kind of feature-dependent weights, which is called attention. So in order to, then the third one, the last one is called message passing mechanism. So there are several architectures in the literature, but we will use graph embedding network, simply GEM, in this talk. So this message passing algorithm is designed to communicate with all neighborhoods. So in the previous 2 net architectures, in order to get node representations, we only get from the neighbors representations. But in this case, we communicate each other in the both directions. So they are sending messages and receiving messages as an information for the node representations. Yeah, so now we are ready to examine the graph neural networks for classification tasks. So we utilize supervised learning to determine whether or not 2 planning graphs represent the same prime 3 manifolds up to homeomorphism. So in order to compare the performance of various networks, we build three models like GN plus GAT and GCN plus GCN and GCN plus GAT. So the names of the models show that the first layer is the shows the first convolution layer and then the second convolution layer. And for a fair comparison, we set all the inside dimensions to be the same, and then we share the common aggregator and NLP classifier. So aggregator plays a role to sum up all the node representations to obtain whole graph representations. And classification layer will give us an answer kind of yes or no. So whether it says they are same or not. So this is kind of flow chart of the GN plus GAT model. So the input is kind of a pair of priming graphs. So two priming graphs. So they are going through the first convolution networks, GN, second convolution networks. It updates the node representation for each graph. And then aggregator will sum up all the node representations to provide the whole graph representations. And then the last NLP classifier gives an answer like they are same or not. Yeah, so for the training data set, we randomly generated all 80,000 pairs priming graphs. So here we say equivalent priming graphs, which means they represent the same three manifold, and equivalent represent different. So, for example, for equivalent pairs of priming graphs, we generate a random priming graph, one random priming graph, and we apply random Newman moves 40 times, up to n max. And then we go back to the original priming graph, and then we again randomly apply the Newman moves 40 times. Then we get two different priming graphs representations, but they are essentially same because they are coming from the same prime three manifolds. And then for inequivalent pairs, we generate two random priming graphs and then apply the Newman moves up to 40 times. Then for the test data set, we prepare 10,000 pairs of priming graphs, which is quite similar to the training data set. But the test set 2 and 3 is more difficult one for networks because it's generated by the number of Newman moves up to 60 and 80, which is the networks didn't experience in the training process. And then the last one, test set, is very interesting because usually the Newman moves, it's not usual. It is a fact that the Newman moves didn't change the determinant of the linking matrix. So there might be some opportunity for the graph neural networks to learn the graph representations instead of to learn kind of determinant of priming graphs instead of learning whole graph representations. So we come up with this test set 4 to distinguish whether or not these GNN networks properly learn graph representations. So here is the chart, the performance comparison of various test sets of all three models here. As you can see, easily the first model, GN plus GAT, significantly outperforms than the others. And here in this chapter, we have two interesting points. Firstly, the performance on test set 2 and 3 is not drastically dropping comparing to the test set 1, because test set 2 and 3 has much larger number of Newman moves than the test set 1. And then this interesting this somewhat counterintuitive property holds even for GCN plus GAT and GCN, and they are why they have low accuracy on the first test set. And then the second point is that performance of the test set 4, For the first model, we have like high accuracy on test set 4, but the other two models has very low test set 4. So it means that GCN plus GCN model, GCN plus GCN model might learn determinants of planning graphs instead of learn proper graph representations. And the first model and second model use graph convolutional mechanism and graph potential mechanism. They are not using message passing mechanism, but the first one, GEN, is use kind of message passing mechanism. They have GEN of graph embedding network. So it means that message passing mechanism perfectly matches well to learn graph representations. And in general, the message passing network, for example, like SGEN, has much more weight parameters than the other models, GCN and GAT. So we have tested like GCN, the other two models, by increasing number of weight parameters and then with longer training phases, but it didn't improve any performance at all. So it means that the message passing mechanism is perfectly matches well to our graph neural classification task. And also we have also tested GN plus GN, which is so message passing mechanism so important. How about we combine two message passing algorithms, but GN plus GN doesn't is underperform the GN plus GT. We don't know why. So that's one of the interesting points.
I mean, usually some particular networks are more better than other particular networks for certain tasks.
Yes.
Graphs. For instance, if you need to know whether certain local sections of the graph interact with each other,
Yeah.
then I think GCN is probably better than other things. But if you want to know the shape of the graph, that's something else. Do you have
the model
is better?
the GN model is better than the others.
For topology.
Yeah, for the topology classification problem. But if we use many GN models, then the message passing mechanism, they update null representations too much, then it will be all the null representation will be similar. So that's why the GN, I think that's why GN plus GN didn't overperform the GN plus GAT. So yeah. Okay, so this is the usual supervised learning utilization for the classification problem. And secondly, we utilize reinforcement learning task. So unlike supervised learning, reinforcement learning has agent in the environment. So the agent interacts with environment by taking actions, then it immediately gets the reward. It updates the agent and the state. It moves on to the next state. So let us define how our RL environment is defined. So like the state space, first of all, the state, so just the prime graph is represent one state. So the state space is actually infinity. And we define some kind of relation in the state space. Like we say that for two equivalent states, so two equivalent states in two equivalent priming graphs, so one is said to be simpler than the other, which if some function f of S1 is smaller than f of S2, then what is f? F is is essentially the sum of the number of nodes in the priming graphs and the sum of the absolute value of the all weights of nodes. So, and then the 5 is just experimentally chosen in our setting. In this way, we can say that we set up our goal to find out the simplest priming graph from a given priming graph by applying 3 types of Newman maps. Then using this F function, the simplest priming graph is unique. So that's why we define this F function. And then the action space. So one action is just one Newman move. So as I said earlier, there are 5 types of blow ups and 5 types of blow down moves. But blow up moves is always available to any node on the priming graph. Blow down is not always available. So there are some kind of level actions. So in order to avoid too many level actions, we incorporate all the blow down move to the just one move. So if one of 5 types of blow down moves is available, then we take this action. So we have like 6 types of actions, so 5 blow ups and 1 blow down. And then the reverse. Since we are aiming to get the simplest representation as soon as possible, we give some penalty at each step, so minus f of s. So the function f reveals shows kind of how simple this priming graph is. So we are providing this penalty of minus fs, and there are some level actions, so we penalty twice, like minus 2fs. Then the reinforcement learning algorithm is designed to maximize the total return. So sometimes the RL agent must sacrifice the immediate period in order to maximize the expected total return. So, for example, these 2 priming graphs are equivalent. They are related by some sequence of Newman maps. I think 6 number of Newman maps. But here, from the left, there is no level blow down move. So you have to blow up to some node such that the resulting priming graph has level blow down moves. So this is the example, but we will see how our trained RL agent works on this example. So there are, among various deep RL algorithms in the literature, we are trying the asynchronous advantage vector critic, shortly called A3C algorithm. So it has like global network, global agent, and it has like several local agents. So the local agents, they are interacting with its own environment, and it's updating itself, and then it updates the global network asynchronously. In this way, we can reduce some in this way we can reduce like computing resource, and then it learns fast. And this network also works in like usual MacBook Air, like for 1 hour. So for each local network has actor network equipment. Actor network defines to the policy function, which is probability of taking which actions. And then creating network is the approximate value function, which is essentially the expected total return from a given state. So here's the workflow of the actor network and creating network. So they have the same structure. So we just use GCN network, and replacing this GCN with GEN or GAT doesn't improve the performance too much. So GCN, we find that GCN is enough for this A3C algorithm. So actor network, creating network has the same input. So this is the current state, so priming graph. Then it will provide policy function and value function. So here is the performance comparison of the A3C networks with deep Q network, which is one of the fundamental deep RL algorithms. So the left figure shows that the accuracy of the two RL agents, as you can see, the A3C is outperformed the DQN, and also when the initial space is created by more number of Newman moves, then DQN shows drastically drops. The accuracy of DQN drastically drops as the number of Newman moves increases, but A3C keeps its accuracy around 90%, over 90%.
How do you compare that? Abbreviations with the whenever it's taking the expected deployment move, or
Okay, so let me explain about the episode of this study. So for the initial state, we generate random planning graph and then take apply Newman moves like 15 times. Then the episode is communicated when the planning graph, the state at the end of the end state is simpler than the originally generated planning graph. And then it terminates also when the number of actions exceeds like 50. So in this case, yeah, so we test like for 100 times for different planning graphs, then it stays in curves like this. And then this shows the average time, the number of Newman moves. So like the initial state we generated with 100 number of Newman moves. The A3C needs like around 130 moves, but the QN moves like more than 200 moves. So it says that A3C is smarter than DQN. They know how to apply Newman moves to which node of the planning graph.
this includes when you go back, right, the arm down.
It's moving down.
Only inputs,
Yeah, to get the simplest version.
so it does not go up and down.
Let's not go up, and yeah, sometimes it should go up for
That's also in the action space. Return.
yes. So this graph actually shows how they apply the which Newman moves. So this is the fraction of Newman moves for this train agent. So those 5 moves flow up moves, and the 3 moves are flow down moves. So for pre-trained H3C agents, they apply all the Newman moves uniformly. But after post-trained H3C, the agent performs like much more flow down moves than the flow up moves. But flow up moves have still small fraction. They are not zero. So they have sometimes increased the number of nodes of planning graphs, and then maybe the number of nodes smaller. And the reason why we set up our goal to get the simplest planning graph is that in this way we can distinguish whether or not 2 planning graphs are same. Because if we have 2 planning graphs, we utilize our RL agent to the 2 planning graphs, then we get the simplest version of the planning graph. If we compare this 2 planning graphs, if there are 2 planning graphs are isomorphic, then the initial states are equivalent. And then secondly, one can obtain the path of Newman moves for the 2 equivalent planning graphs. So when we get the same simplest planning graphs, then using the history of the actions, then we get the path of Newman moves from one planning graph to the second planning graph. Of course, it is not the shortest path of the planning graph, 2 planning graphs, but it provides us some kind of path of Newman moves between between planning graphs. Yeah, so this is our kind of example, interesting example. So the smallest number of actions needed is just 8. So, but the DQM agent, it did not find the way from the right planning to the left planning. However, the A3 agent, it used 16 actions from the right one to the left. And this is also like a complicated example. Did you see they are equivalent or not? But the supervised machine learning network, the GNN networks, and both supervised GNN networks and RL agents say that they are same. And using RL agent, we can get a pass from one to the another. Over 150. Yeah.
That's the minimum, no? Or that's what the agent?
That's the agent. Yeah, number of actions taken by the agent. Yeah. So yes. So too fast. Anyway. So in this talk, we examine the efficiency of the applying geometric like graph neural networks to the problems of low-dimensional topology in a very simple setting. So we only considering the planning trees. So this, from the planning tree, we only get oriented and closed three manifold. But for arbitrary three manifolds, we have to use like generic planning graphs. So generic planning graphs has much more structured data. For example, to each node, there are like 2 integer weights, and all the edges has some kind of signs, and then the planning graphs can have the cycles inside in it. Then in this, for generic planning graphs, so for generic planning trees, there are only 3 types of Newman moves, but for generic planning graphs, we have like, I think 9 types of Newman moves, which is more complicated than this one. So hopefully for future directions, one can utilize such graph neural networks to understand the 3-dimensional topology or 4-dimensional topology. One direct generalization is just to use the generic planning graphs, and then the other way is to use kind of some taped graphs for knot and link diagram. Then we have to consider the 3 types of Newman, 3 types of Reidemeister moves, and then 1 type of Fedorkin moves known as corresponding to Kirby moves. So yeah, so this is a kind of very simple toy model of deciding whether pair of Kirby diagrams give determining or number of Fourier. However, this is the I think first time of application of graph neural networks to the topology and the geometry as well. So I think at some time in the future, there is, I hope that this kind of GNN networks can recognize whole 3-dimensional topology and 4-dimensional topology, or some notch and links. Yeah. Yeah, I think I'm very fast. Anyway, thank you for your attention.